Okay. Oh, why is everyone like looking this way? Oh, right. I had to do a talk, right? Okay. Okay. So, do you know the game I was playing over there right now? Just so I have an idea of how many people are listening to me, raise your hands, please, if you can hear me. Okay, cool. So, my name is Pedro Castilho. You can see my Twitter and my GitHub over there if you want to complain to me about not starting my talk because I was playing Tetris. So, I'm going to be talking about front-end programming with Rust, which by itself seems like a pretty weird idea, right? I mean, everyone knows that if you're doing front-end programming, you should be doing JavaScript. So how can you do that with Rust? And the other piece of the puzzle is the reason why the Tetris game that I was playing only has like 65 lines of JavaScript in it. So the reason it has so little JavaScript is because it is made using WebAssembly. And what exactly is WebAssembly? Well, WebAssembly is a code interchange format. That means it is a format you can use to send code to other people so they can execute it. It is supposed to be an assembly language-like code interchange format, so it's not really an assembly language. Well, why is it not an assembly language? Because an assembly language is defined as being a textual representation for the machine operations of a computer. So when you have WebAssembly, it's actually something that is supposed to run inside browsers. So it's not really an assembly language because it's not related to a real machine. It's actually the machine language in a way for a virtual machine which runs inside of browsers. And just last year, WebAssembly reached the level of a W3C recommendation. The W3C is a nonprofit entity which is formed by volunteers from many companies who decide what should be the standards which dictate how the web works. So if you've ever done anything on the web, like if you're doing stuff with HTML, if you're doing stuff with CSS, those are all dictated by the W3C. So you know who to complain about CSS being so broken now, and you can send some very angry emails to them whenever you want. So why do we need a code interchange format? I mean, I can think of something we have that like already does that, where you can send your code and people can execute it. Oh, yeah, right, JavaScript. So why is WebAssembly needed if we already have JavaScript? If we can send JavaScript to people and people can run that JavaScript inside their browsers? Well, I can think of a few reasons why people might not want to use JavaScript. But okay, if you're an experienced JavaScript developer, you can get around this kind of thing, and you can stop it from happening, so it won't be a huge problem. But there are other reasons. For instance, let's say you have a code base that your company has been using for a long time, and you want to do the same thing except on the web. So how would you do that? You would have to rewrite everything in JavaScript. And JavaScript has a very particular execution model, which is meant to be simple to implement, but to be responsive and to not let the user just keep doing stuff while the page is frozen. So what we can do in order to avoid the problems JavaScript has is to use JavaScript as a compilation target. And that has been pretty successful. I think everyone here knows about some language which is not JavaScript, but which can be compiled to JavaScript. Has anyone here ever used a language which compiles to JavaScript? Raise your hands, please. Okay, cool. So using JavaScript as a compilation target is nice, it works, but for many reasons, JavaScript is a bad assembly language. But it also has some pretty good points. I'll talk about the good points first, and then I'll explain why JavaScript is a bad assembly language. When you minify JavaScript, it is actually surprisingly small considering the amount of data of code you have in there. JavaScript minifiers are very smart nowadays, and they can generate very small bundles from even a large amount of code. JavaScript JITs are very mature, and they can make even very dynamic JavaScript code reasonably fast, so you won't have the problem of it being a slow target. Oh. Okay. But there's also the bad side, which is the only number type in JavaScript is I3E754 double precision, which C programmers know as double. So whenever you use a number in JavaScript, it doesn't matter if you just need an integer, if you just need something else, what you get is a double. And doubles are slow to work with, doubles have floating point imprecision, so that can be a problem. You also get unpredictable pauses because of garbage collection and because of jitting. So whenever your code is running, it can just stop at any time because the garbage collector needs to run and collect a bunch of objects you created. Or the JIT can just decide, oh, I've seen enough code and now I know how to make this fast. So your code just stops running until the JIT can finish doing its thing and you get faster code, which is good, but at the same time, it's a pause and you get unpredictable performance. And JavaScript is in general very hard to optimize, which is the whole reason we need JITs in the first place. Because when you have a language like C, which is a bit more regular, you can just go over the source code, you can figure out how things need to execute, you can look at the types, and you can generate efficient code for that. In JavaScript, there's a lot of things you won't know until runtime. So you need to have a JIT, which is at runtime looking at the code, and it's trying to derive typing judgments and trying to derive places where the code can be optimized and to generate good code. And the JIT even introduces even more problems, because if you have the JIT running, so the JIT can look at a function and it says, okay, I've seen this function like 10 times, and every time the argument has been an integer. So this is probably a function that only takes integers. So it generates code which only works on integers. But what if that function isn't an integer function? What if it can also take strings? So the 11th time the JIT sees the function, it will try to run that fast code, but you actually gave the function a string. So what happens then is what is called a de-optimization, which is when the JIT says, okay, I was wrong. So let's throw this fast code away and look at this function more until I can decide what the hell this is. So that's a problem, because you might have a function that like it should run fast, but the JIT can't decide what to do with it. In general, JavaScript performance is very hard to predict. It's a very difficult job to try to make performant JavaScript code. So we need something better than JavaScript. And the first attempt at making something better than JavaScript to use as a compilation target was what is called AwesomeJS. AwesomeJS was a standard which was proposed by Mozilla and which was supposed to be a subset of JavaScript. So you take out of JavaScript everything that cannot be easily optimized, and you just have a little language core which has only operations which can be optimized easily and which has type annotations. So if you pay attention to this code, you will see that there are a lot of places where, like, for instance, you have I plus 12 bitwise or 0. So that seems like a very weird thing, especially because, like, if you know about how bitwise operations work, anything or 0 is itself. So why is the reason that we do this? Because the way bitwise operations work in JavaScript is that even though the only type of numbers in JavaScript is double precision float, when you do a bitwise OR, it actually converts both arguments. It has to convert both arguments into 32-bit integers, and then it does the bitwise OR on those 32-bit integers. So in awesome.js, a bitwise OR 0 is actually a type annotation, which is telling the awesome.js compiler, this is an integer and this will always be an integer. So if you look at this function, it doesn't really look like the kind of JavaScript you would write, and that's because it's not that. It's supposed to be generated by tools which generate JavaScript, and it was actually reasonably successful. This is also awesome.js, and you can see like it's differentiated by that use awesome declaration in the beginning, just like you can say use strict if you want stricter checks. You can say use awesome, and if the browser supports it, then your JavaScript will be parsed as awesome.js, which will be supposedly better optimized. And Yeah. And if the browser doesn't support that, it's just a random string. It just gets ignored, and that's it. So as.js is easy to optimize, it's easy to generate, and it can be even smaller than JavaScript when minified because you're doing less kinds of operations and you're doing mostly operations that minify well. But it's still not a perfect solution. So let's look at how JavaScript executes. When you get some JavaScript code, you need to parse the JavaScript, then you need to compile it, because even though JavaScript is a dynamic language and a lot of people will call it an interpreted language, JavaScript is actually compiled by every browser which handles JavaScript. So there is a compilation time, and then it starts executing. You will have a few GC pauses, you will have a few JIT pauses while they are collecting trash, while they are trying to make the code more efficient. And as Node.js, as it is a subset of JavaScript, and it is still executed by the same JavaScript engine, just with better optimizations, it has those same problems. You still get unpredictable garbage collection, you still get unpredictable jitting. And there's a different problem. So now you can optimize your code a lot more, which is nice. Everyone is happy about that. But now, actually parsing the code becomes a bottleneck, because JavaScript is not really a simple language to parse, and even though everything in the JavaScript engine can be optimized, the parser is actually reasonably slow. And AwesomeJS was only really fast in Firefox, because Mozilla were the ones pushing AwesomeJS as a standard, and they were the only people who actually cared enough to have a decently efficient implementation of AwesomeJS. So what do we do now? Well, we use WebAssembly. So with WebAssembly, we get rid of the whole parsing problem, because WebAssembly is a binary format. And it's a binary format which is designed from the ground up in order to be very efficient to parse. Not only that, but WebAssembly allows for incremental parsing, which means that you don't have to parse the entire file before you start executing it. So with JavaScript, you need to parse the entire file which gets sent, then that gets compiled, and only then will it be executed. With WebAssembly, you can get just like 10% of the file, and you start executing while you're still getting the rest. WebAssembly is, in general, 20% smaller than minified.js because, once again, it is a binary format. And besides being fast to parse, the other main goal of the WebAssembly format is to be very small. So it can be sent over the internet, and it can not be a huge bandwidth hog. And WebAssembly has no garbage collection at all, which can seem like a bit of a problem. And we will talk about that in a second. But for now, let's just consider that having no garbage collection means that you get no unpredictable pauses while your code is running, and you can know that whatever you write will run exactly as it is written. And we don't get the problem we had with AwesomeJS, where only Mozilla really cared about AwesomeJS, because all major browser vendors, Microsoft, Apple, Mozilla, they have all agreed that they will all support AwesomeJS. And in fact, all the major browsers already support AwesomeJS. I think the last time I checked, around 85% of all internet users already had AwesomeJS support, which is not great, but it's going up fast. So comparing the WebAssembly execution with JavaScript, the JavaScript, you need to do the parsing up front, you need to do the compiling up front, and then you get the GC and JIT pauses. With WebAssembly, you can start parsing. While you're parsing, you do decoding, because you don't compile WebAssembly, you decode. WebAssembly is designed in such a way that every WebAssembly instruction should be like 1 to 3 actual machine instructions. So you just need to take every instruction and say, okay, these are the instructions for that WebAssembly instruction, and so on and so forth. And you can theoretically do all of that in parallel. So like while you're still parsing, you can start decoding what's already parsed, and you can start executing what's already decoded, which is great. In practice, I think no browsers are actually doing parallel parse, decode, execute right now, but it should be coming to the next versions of Firefox and then probably to Chrome. So this is what WebAssembly looks like. Like I said, it's a binary file, and you can't really read anything from it except for like the magic number at the beginning, which is just ASM in ASCII. You can also convert this into a text format like you can with most assembly languages. And an interesting thing here is that you can notice that WebAssembly is actually a typed assembly language. You need to declare the types you use in the code up front, which is pretty interesting because it allows you to convert WebAssembly into other languages, which can be something interesting in the future. I haven't seen a lot of tools exploring that right now. But anyway, fun fact, this text format for WebAssembly has possibly what is the best file format of all time, because it's called WebAssembly text, or for short, what? Anyway, the point I'm trying to make here is that WebAssembly is supposed to be something useful for when you need predictable performance, when you need small file size, and when you need something that runs fast. And an interesting thing to notice is that right now, the way WebAssembly is specified, you can't use WebAssembly as the only scripting language in your app. You actually need JavaScript to call into WebAssembly functions, which will then run. So WebAssembly is supposed to be a complement to JavaScript. So JavaScript excels at being responsive to the user. It excels at scheduling a lot of concurrent things, even though it's single-threaded, while WebAssembly is good at running a lot of sequential instructions, and you go into this heavy function, and it does that really fast. So it's supposed to be a complement to JavaScript. It's supposed to be strong where JavaScript is weak, and not to replace JavaScript. Still, if you do a little bit of effort, WebAssembly can help you use a lot less JavaScript, which is good news because I know a lot of people who hate JavaScript. Anyway, I'm not going to go into every single instruction of how WebAssembly works, because I know most people here would hate me if I was explaining every single instruction. But you can go to this github.io page, which is actually an official page from the specification project, and you can see how it works. But, so let's go a little into what WebAssembly changes inside the current JavaScript engines. So JavaScript engines are single-threaded. That means that you only have one instruction running at every single time. So let's say if you have console.log foo, that runs, and in a console somewhere foo appears. If you have document.onClick do something, well, that's a little different. So we also have the event handlers. And this will add an event handler which says, okay, whenever someone clicks the document, you run the do something function, whatever that is. So let's say you have another event handler that says when you click on some div, you run do another thing, and so on and so forth. And finally, we have the famous JavaScript event loop, where if you click on the document, you get do something in the event queue. When you click on some other div, you get do another thing. Some event handler goes in. So the event loop is just this. Events happen, stuff goes into the queue, and it goes into code execution as soon as possible. So this is just vanilla JavaScript. The only thing that changes in this part until now with WebAssembly is that JavaScript has no way to know what these things in the event queue are. So they would always be like JavaScript functions, which would go into the JIT compiler, and it would then run. But now any of these can be actually a WebAssembly function. So when that happens, the execution goes away from JavaScript, and it goes into WebAssembly, and WebAssembly will run, and then it will hand the control back to JavaScript. But WebAssembly can't really interact with JavaScript. Not right now. In a way, WebAssembly is sandboxed, and there is a proposal to change that, but it will probably only go in like next year. So, oh, right. And one more thing, you have the heap, which is like if you have objects and they will be dynamically allocated and they live on the heap. Once again, WebAssembly has no access to this, and it can't touch anything that is on the heap. So if WebAssembly doesn't have access to the same variables as JavaScript, if it can't touch the JavaScript heap, so what can WebAssembly do? And this is the new thing. We now have the WebAssembly memory. So this is just like a gigantic array, really. It's like a real computer memory, and it's really just a gigantic array which WebAssembly can mutate. So whenever a WebAssembly function starts running, the JavaScript engine says, okay, there is a WebAssembly function running. WebAssembly function, how much memory do you need? So the WebAssembly function will declare its memory size, and the JavaScript engine just hands it a piece of WebAssembly memory, which it can mutate in any way it wants. And the only mechanism really for communication between JavaScript and WebAssembly is this memory. So WebAssembly can only write and read from this memory, and JavaScript can write and read from it. So it's reasonably bureaucratic to actually get any data from JavaScript to WebAssembly and vice versa, because you need to write that data in the format that WebAssembly expects, and WebAssembly needs to read it. And this memory, as I said before, is not at all garbage collected. Anything you write there, it lives there until the end of time, possibly. And, okay. We don't have a garbage collector, so what can we do? Do we manage our memory manually? That is possible. We could use something like C or C++, where you actually need to say, oh, free this, and then we would have a specific allocator for WebAssembly, which would know how to delete stuff from WebAssembly memory. But that's a pain in the ass. And you get a lot of seg faults and memory corruption until you actually get something to work. Also, C++ is a gigantic language, which I don't know how anyone really learns that. And I think most C++ programmers really only use like 50% of the language because there's stuff in there that is really like arcane. So the solution I will be talking about today will actually be using Rust. Who of you guys has heard about Rust before? Yeah, I was very happy yesterday actually because there was William's talk, and he was talking about Rust, and he explained a lot of things. And I was really worried about this because Rust isn't really like a massive language or anything like that, but it has some fairly unique stuff like the borrowing system and stuff like that. And I was worried, oh, I'm going to show some Rust code to people, and they are going to be like, what the hell is that? But I think since he explained some of the basic concepts, it should be a little bit better. So this is the description on the official website. Rust is a systems programming language that runs blazingly fast, prevents seg faults, and guarantees thread safety. And I know that sounds like big marketing claims and stuff like that, but most of it is actually pretty true. There is no such thing. I have never seen a seg fault in Rust unless you specifically say, hey, I'm doing something that can cause a seg fault. So Rust has no garbage collection, just like C and C++. But you don't actually need to do manual memory management because it has the ownership system, which means that at compile time, the compiler actually knows when anything you allocate dynamically will still be used or will not be used anymore, and it can automatically insert the memory management code for you without you having to say so manually. The general idea behind Rust is that you should have low-level control but high-level ergonomics. So even though Rust generates very low-level code that would be comparable with a language like C or C++, it has many language features like pattern matching and a lot of advanced user-defined types, which can be used in ways which you only see in languages like Haskell or something like that. And what I think is actually the main factor for using Rust to generate WebAssembly. Rust has a very, very, very small runtime, and you can make it even smaller, because the only thing Rust really needs is a memory allocator. You can do it like zero runtime because C can do that, but they have the advantage that their allocator is inside libc, which comes with your operating system, so they're kind of cheating there, and that doesn't really count. Anyway, another big advantage about Rust is that you have an actual package manager. Because C and C++ are from before the internet and stuff like that, so you couldn't really have a package manager. You need to like copy stuff manually, and I think like every time you need to use a new library with C or C++, you lose a few days just trying to get it to compile. So with Rust you have Cargo, which is among other things a dependency manager, which will get the libraries you need for you, install them, build them, and you have no pain at all. And there's crates.io, which is pretty much NPM, but for Rust. Okay, so I'm going to, oh, okay, I lost. Anyway, So, like I said, the Tetris game I was showing is actually just like 65 lines of JavaScript. Is that right? Yep, it's exactly 65 lines. But there is a trick to that. So instead of actually doing the whole game in 65 lines, I'm actually calling into WebAssembly, which has been compiled from Rust code. So if you look at the code, it's actually really not that big either. We have like 460 lines of Rust code, which is implementing the whole game. So I'm going to try to walk you guys through like how I did this. Actually. So this is the initial version of the project, which I changed it to. And you can see that the initial version, it just prints an alert. So how are we doing this? And now I'm going to go over a few tools Rust has to make it really easy to work with WebAssembly. So just to show you, this is pretty much all I had to do to get to this point. So we have cargo generate, which is a tool you can install, which it becomes a subcommand for cargo, which allows you to generate new Rust projects from a Git template. Then we do an npm init, and npm actually already has first-class support for WebAssembly. So if you say npm init wasm app, it actually creates a new WebAssembly app with everything ready for you. And you have this really cool tool from the Rust WebAssembly team called wasm pack. The idea of wasm pack is that it will take your Rust code and it will turn that into WebAssembly and all the auxiliary files you need in order to have a package ready to publish on npm, which you can just go there and say npm publish and everything works. It's pretty amazing, really. So, yeah, I thought I was going to have to do more stuff, but actually that's pretty much it. So let me just show you the code. So this is it. And I think that's really hard to read. Okay. But anyway, the main idea here is that we're using wasm bindgen, which is a Rust library, which will automatically generate bindings from JavaScript into WebAssembly. So the idea here is, like I said, it's very bureaucratic in a way to actually get your code to work to get your code to work with WebAssembly in your JavaScript, because you need to write that data into the WebAssembly memory in the format that WebAssembly is expecting to read it. And it's really just very tiresome. So Rust actually has a library called wasm bindgen, which if you annotate any function with like hashtag wasm bindgen before the function, it will actually, when you run the wasm bindgen command line tool on the wasm file that gets compiled, it generates a JavaScript file, which has all the functions which do the work of like copying stuff into WebAssembly memory, copying stuff out of WebAssembly memory, and just getting things around where they need to be. So one thing I want to talk to you about through this Tetris example is the idea of how to design an API for WebAssembly. Because, okay, copying from and to WAS memory is the most expensive thing you're going to do while working with WebAssembly. Because WebAssembly itself is pretty fast. But the WebAssembly memory, it's sort of a sandbox inside of which WebAssembly can read data and write data. And there's a cost to copy that data into the JavaScript memory and vice versa. So you want to avoid that as much as possible. So what's the idea with my little Tetris program over there? The general idea is that I only do one copy every frame of the game. So you have 60 frames per second. I'm only doing one copy when I need to render. So all the data actually lives inside the WebAssembly process. And only when I need to copy it, I call from JavaScript a function generated by wasm bindgen, which runs the game loop and then it reads that data from the WebAssembly memory and hands it over to JavaScript for JavaScript to render the actual game state on the screen. And that is pretty much how you should be designing your APIs between WebAssembly and JavaScript. You should be trying to minimize copying as much as you can. If you actually should be passing a large object from one side and another, one thing about the game, the little Tetris game you're seeing, and this is a trick I actually was inspired by the official WebAssembly tutorial from the Rust folks. You see? Yeah. So the little Tetris game you see here, it's actually a string. Those are Unicode characters, and they just get printed into a element, so they align. And the only thing I'm really doing every frame is passing the string from WebAssembly to the JavaScript process. So that is very efficient, and it's a very good use of copying. But if you actually have a process where you need to pass a large object between JavaScript and WebAssembly, you shouldn't really pass the object. Instead, you should have some kind of handle logic where you can say, okay, I just passed the ID of this object to JavaScript, and JavaScript can compute stuff based on the ID only. And JavaScript can tell Rust, okay, do something to the object that has this ID, this handle. Anyway, just summarizing everything I said, WebAssembly is a complement to JS, which offers predictable performance and a fast startup time. So the main problem we have with JavaScript is that you don't know how the actual execution of your code will be. You have garbage collection pauses, you have JIT pauses, and you don't really know what will happen when your code runs. WebAssembly has its own little memory space which it manages, and which never gets shared with JavaScript unless JavaScript explicitly says, okay, I want to read this, I want to write this. And WebAssembly can't really get JavaScript objects, get stuff on the heap, and say, okay, I want to use this object. But that will probably change next year, because there is already a proposal which is likely to go in. And finally, and this is something I can show you about this game, since you only have functions in WebAssembly which get called by JavaScript, you can't really okay. Is it easier to read now? Is it okay? Okay. So you see here, like, okay, so you see here that I annotate these functions. So you can see that I actually annotate these functions with AwesomeJS. So this is actually telling Rust, okay, I am going to call these functions from JavaScript, so generate a JavaScript interface for them. So the actual file it generates is here. Yeah, so you have this file. I did not write this. This was generated by Rust. And so you see here, like I have, let's see, render frame. Yeah. So actually, the actual render frame function, which was generated by JavaScript, it uses these functions, which are all defined by AwesomeJS, and to manipulate the Rust memory and actually get stuff from it and pass it to and actually be able to use it from JavaScript. So you don't need to worry about any of that, because AwesomeJS will take care of that for you, and you don't need to do it yourself. So while I was making this program, I found something out. People who watched Williams talk about making a game in Rust yesterday will remember that if you want to use random numbers in Rust, there's a library called rand which does that. That library is not compatible yet with AwesomeJS. If you try to compile it, it will give you an error saying such and such function does not exist, because it depends on operating system primitives, which obviously do not exist inside the browser. So what can you do? So AwesomeJS doesn't just let you export functions so you can use them from JavaScript. WebAssembly supports importing JavaScript functions so you can call them from WebAssembly. So what I did was, since I can't use native Rust random functions, why don't I just use math.random from JavaScript? And it's what I did. So you define inside an external block, and bear with Rust for a minute here because this FFI was originally made to interface with C functions, so that way you need to use like an extern C, even though I'm interfacing with JavaScript. And I just annotate this function, which I don't define, with wasm_bind_gen JS name equals random JS namespace equals math. And whenever I call it from Rust, this will actually get compiled into a call to math.random from JavaScript. So this way I could get around the problem of not really having a random number generator, and I just use the JavaScript random for this. It's also very helpful for debugging if you can use console.log, which is just what I did here. Anyway, so yeah, I hope you can see how convenient wasm_bind_gen can make it to work with WebAssembly from Rust. But there's a different problem here. So okay, we can use WebAssembly, we can generate WebAssembly, but what about the bundle size? Will WebAssembly be small? So if I run here. So if I actually do a compilation here, and I check the sizes of the generated file, so you can see the actual file is the wasm Tetris bg.wasm, and the whole game fits into 22 kilobytes of WebAssembly, which I think is pretty reasonable, but we can actually make that better. So, and just gonna show you something. So the reason this compiles to such a small file size is because you can just say in your cargo file, which it dictates how your Rust code gets built, that like you don't want debug symbols, you want link time optimization, and you want to optimize for size. So doing all of that, I actually reduced what was originally a 160 kilobyte WebAssembly file to 22 kilobytes. But there are still optimizations that Rust can't do by itself. So I think the final thing I want to show here is a tool which was made by the mscripting project, which is also pretty cool, and you should look into. It's a C++ compiler to WebAssembly, which is wasm_opt. And I actually ran it before on the generated file, which is wasm_tetris_bg.wasm, and I got wasm_tetris_bg_opt.wasm, which it actually cut 3 kilobytes more out of the file. So I think it's pretty cool that we can implement an entire Tetris game in just 19 kilobytes of WebAssembly. And I think if you count like the JavaScript wrappers and everything, this whole project came up to like 23 kilobytes, which I think is pretty reasonable, right? Anyway, I'm almost out of time here, and there are a few tools which I would like to talk about, but I didn't have enough time in the talk, so I'll just mention them, and I hope some of you will want to look into them. So you have wasm_bind_gen, which I talked about. You have wasm_pack. You have wasm_opt. You can use all of those to get like your WebAssembly bundles out very easily. You can decrease their size. And Webpack itself, it can handle WebAssembly without no configurations. It's already ready for WebAssembly, and it can bundle WebAssembly just like it would do with JavaScript. So one tool which I didn't get to talk about is Twiggy. Twiggy is a size profiler written completely in Rust. The idea with Twiggy is that you can say, Twiggy profile some WebAssembly file. And it will tell you what functions are inside that WebAssembly file, how big is each one, and why did each one get included. So that way you can refactor your WebAssembly APIs in a way that you eliminate what is making your bundles bigger and actually get a very small bundle. And one thing I think is really cool is U. So U is this web framework, which is very much like React and Redux, or like Elm if you've used that. But the main difference it has is that it uses Rust's parallelism primitives. So you actually get to do like a multi-threaded front end. And the way it does that is that Rust actually supports compiling threads into web workers using WebAssembly, which I think is really awesome, and you should probably look into it. So anyway, thank you very much, and I hope some of you will feel inspired to use WebAssembly in your future web work. Oh, and you can check the source code for my little Tetris game at... Oh, they actually took it out. Anyway, it's in my GitHub, and you can check it whenever you want. It has a really gross hack where it has no game over, and it just crashes if you lose. Okay, so he just told me I have time for questions. Does anyone want to ask anything?
I would like to know about, do you talk about the performance between copying data from the WebAssembly memory and to JavaScript? I would like to know if you have some application examples that someone is doing, is getting benefits from using WebAssembly, some applications that is getting benefits.
Okay,
and,
so actual uses of WebAssembly.
And so if there is some profiling tool to investigate the performance, I'm losing much time with this, what I'm gaining is the trade-offs.
Okay, so the main way to actually profile WebAssembly code for speed right now is to use the browser's performance primitives. So you have a function called performance.now, which gives you high precision timestamp. So you can use that to figure out how much time you're taking doing something. And that's the main way to profile WebAssembly code right now. It's really manual, but as WebAssembly code gets more acceptance, we will probably get like better tools for that. I know there are a lot of people in the Rust working group for WebAssembly who are working on tools for speed profiling, so that should get better from now on. And about applications which are actually getting gains from WebAssembly, Mozilla actually has a post where they took their source map tool, because like when you use a language which compiles to JavaScript or to WebAssembly or whatever, if you want to debug that and you want to know like what line of code is running right now, what line of code is breaking, you need to have a source map, which is this standard file which says, okay, this byte came from this line of code, this byte came from that line of code, and those files are usually really big and reasonably slow to parse. So Mozilla actually rewrote their source map tool using WebAssembly, and I think they had like a 30% speed up. It was pretty good. It was pretty good. Anyone else want to ask anything?
Oh, thank you. So you talked about how WebAssembly has no garbage collector. It's kind of like those calls that the language itself puts over there to free and allocate memory. So I don't know the exact definition, formal definition of garbage collection, but what is the difference between a real garbage collector and just the language guessing where to free memory?
Okay, so a garbage collector, it means the programmer doesn't really need to specify how data will be used. When you have Rust, you have what are called lifetimes. Whenever you have dynamically allocated stuff, that variable has a lifetime. Usually the compiler can like infer the lifetimes itself and figure out where a variable needs to be freed, but sometimes you can explicitly say, I need this thing to live as long as that thing, so it actually inserts the free calls by itself. The difference between this is that a garbage collector, it runs at runtime. At runtime, you have something that is like looking at every variable and saying, okay, is this still in use, is this still in use, and this still in use, and eventually it will free that. That's the general idea. Do we still have time? Okay, so we're done. Thank you very much, everyone.